Hi friends, we are going to see how to perform ESP or external static pressure calculation. In this project, chilled water from air cooled chiller is supplied to different FCUs located for different rooms. We will take one FCU from here and perform the ESP calculation. And I'm going to consider this FCU which is located in the lobby area. So first the FCU is supplying 431 liter per second, and the first we have one branches which has 108 liter per second, and we have one supply air diffuser, and after that we have one reducer here. Actually, if you see from top view, it is a reducer because if you see the duct dimension 450 by 250 here, the main duct. After this branch take off, the duct size is reduced to 450 into 200. So 431 minus 108, 323 liter per second we have at here this point. After that we have another branch that is 108 liter per second. So we have one reducer here. So it will be 215 liter per second after this branch take off, and we have one more branches that is 108 liter per second here, and we have the final branch which is supplying to this point, that is 108 liter per second. So we have different supply square diffuser 1, 2 and 3, 4. So same we have the return diffuser also 1, 2, 3 and 4. So first we are starting with the straight duct which is after the FCU. So this length before the reducer to the FCU, so this length it is 500 mm or 0.5 meter. Generally for the ASP calculation it's very simple. There are only two formulas we have. So for the straight duct, if you have for example head loss in Pascal is equal to friction loss, that is Pascal per meter into length of the duct. This is applicable to all the straight duct, okay. And the second only for the fittings. So fitting also, whatever the fittings, elbow, reducer, whatever the fittings, we have one common formula, that is head loss in Pascal is equal to velocity pressure. Here the velocity pressure will come, velocity pressure into fittings coefficient. So fittings coefficient normally we can get from the ASHRAE duct fitting database, otherwise you can get from the SMACNA also. So if you apply this formula you can get the answer easily. So in our case, the duct size is 450 by 250. As I told you, the airflow is 431 liter per second, which is coming from the FCU. And FCU to first branch, as I told you, 500 mm or 0.5 meter. So coming to the friction loss, in the duct sizing video, I explained clearly about the friction loss for the FCU duct, staircase pressure duct, FH duct, AH duct. One by one, I explained in the duct sizing video. Please have a look at that if you have not watched that video. So friction loss for the FCU duct, we consider 0.6 Pascal per meter or 0.08 inch per 100 feet. So you know the duct sizer. So if you go to the duct sizer, for example here the airflow for in our case is 431 liter per second, and the head loss I'm going to follow 0.6 Pascal per minute, and the duct size already which is given in the calculation is 450. So 450 by 250, if I apply 450 it will automatically come 250. So width and height is given. So if you see this answer here, what is the head loss they have given? 0.595 Pascal per meter. The unit is very important, 0.595 Pascal per meter. So the same I applied here, 0.595 Pascal per meter. This is a screenshot, and so I'm going to apply the same 0.595 for the friction loss into length of the duct. So length of the duct is 500 mm or 0.5 meter. So the unit already here, the head loss is 0.5 Pascal per meter. That's the reason I applied the value in meter also here. So if you multiply both the answer, you will get 0.30 Pascal. That is for the straight duct. And coming to the second one, so once the straight duct is done, that is this one is done, we have one reducer and we have one again straight duct. So first we will finish this straight duct and we will come back to the reducer here. After the first reducer, the flow become 323 liter per second from 431 liter per second, and the duct size as per the drawing is 450 by 200. So again we will go to the duct sizer. So I'll enter 323 liter per second, that is the flow. Head loss is 0.6 Pascal per meter, and here the duct size, for example in this drawing it is mentioned 450. So the answer height will be 200 automatically, and the head loss is 0.632 Pascal per meter. So you can see here the head loss, that is 0.632 Pascal per meter. I'm going to apply the same 0.632 Pascal per meter into the total duct length which I mentioned in the drawing is 3 meter. So the answer will be 1.896 Pascal. Now we have completed this straight duct and this straight duct also, and we have two more straight duct, that is at this point at 3 meter and this point it is 5 meter. So first we'll finish the straight duct, we will see one by one volume control, damper, fittings and everything. So after this reducer, the flow at this point is 215 liter per second and the duct size is 350 into 200. So now the straight duct again. So duct size is 350 by 200 and the flow is 215 by liter per second. So if you go again to the duct sizer, you can see this is 215 liter per second and the friction loss 0.6 and the duct size is 350 and 200. So the head loss here is 0.526. The same I applied here 0.526 and the duct length is 3 meter. So total it will be 1.578 Pascal. And coming to the next straight duct, that is the flow is after the reducer, it is 108 liter per second. So friction loss is same and the duct size it is 300 and you will get 125. 125 is not available duct size, so you have to make the next value 150. So now the friction loss is 0.449 Pascal, which you see here 0.449 Pascal per meter. Okay, so that I need to apply here for the calculation. 0.449 into the length is total length is 5 meter. If you can see the duct drawing here. So here now it is 5 meter. 5 meter. So you have to multiply with this 5 meter to get the total pressure drop. Total head loss. So it is 2.245 Pascal. This is what total strike duct we have calculated now. Now one by one fittings we have to start. So the first fittings what we have here is the from the FCU it is the reducer. So if you see at this point the reducer is there. So 450 by 250 one size and the next size is 450 by 200 because of the reducer. Actually from the top view of the duct you cannot see the reducer clearly because the reducer here is reduced in the height point of view. For example here 450 width and here also 450 is the width, but if you see the height it is 250 and here it is 200. So the reducer is reduced in the height, so you cannot see from the top view. But if you see here at this point the reducer it is reduced in both the width and height, so you can see the reducer in this angle is very clear. So for the reducer, the airflow is 323 liter per second. The size at upstream 450 by 250. The size at downstream it is 450 by 200. I am talking about the reducer like the incoming and outgoing flow. That is 450 by sizes 450 by 250 into 450 by 200. And the friction loss I am going to apply the same one. The formula here is different. That is head loss is equal to velocity pressure. This is the new term for the fittings, but for the straight duct this will not come into fittings coefficient. So this one you can take from the ASHRAE application handbook you can take. So the velocity pressure, how to find out? The same duct sizer you can go here for example, and here the flow is 323 liter per second and the friction loss is same, and the duct size for example it is 450. If you apply the 450 here, 450 by 200. So here you can see the velocity pressure this time which is here. You should not take the head loss. Head loss is only for the straight duct. For the fittings you have to take the velocity pressure, that is 9.5. So I'm going to apply the same here 9.5. And the second important thing is the fitting coefficient that you have to take from this ASHRAE application data book only. For example, if you want to take the fittings coefficient, you have to know two important value. That is the theta. The theta means the angle. That angle you can see. This angle is vary for the different length, and the second one is A0 by A1. So first let me explain what is A0 by A1. So size at upstream is 450 by 250 and size at downstream is 450 by 200. So if you see the area 1 is equal to width into height, that is this is 450 in mm, so I just convert to meter. 0.45 into 0.25, that is 0.1125 meter square. Similarly for the downstream it is 450 by 200, so 0.45 into 0.2 it is 0.09 meter square. So A0 by A1, you can see the calculation, it is very important. A0 by A1, so if you divide both you will get 1.25. so here we are at this point 1.25 because here it is 1 and here it is 2, so we are between these two, so we can take the average value 1.25. and the second important thing is angle here, the theta. So how to select the angle, because this angle is very important. Based on the length this angle will vary, so I will show you one example here how it will vary. So if you see at this point and 450 by 350 duct size I have mentioned from the top view, 450 by 250, and coming to the next size 350 by 200, just for the example I have given. So if you if you fix the length like 417 mm, you can see how the angle is coming 14 degree. You can try in the AutoCAD also. And second, same size, I have not changed the size here also, but what I changed here is the duct length I have increased, I mean the reducer length. Earlier it was 417 mm, now I increased to 428 mm. You can see how the angle is changing here. Earlier it was 14 degree, now it become 13 degree. And if similarly if you increase, again I increase the duct reducer length from 428 to 715 mm. I randomly increase the reducer length. It's not a fixed one. I'm just changing for your example only. Now you can see what is the angle here is 8 degree. Earlier it was 14 degree, then 13 degree, now it is 8 degree. So the concept here is if you increase the reducer length, this angle will become low. So initially for any project we consider the reducer length normally 300 to 400 mm. So for the higher duct sizes you can increase the reducer length to 600 mm also, that is not an issue. But if you increase the reducer length, the angle will be reduced as I showed you. So the, in our case now I consider the 400 mm because normally this is practically changed because of the site condition. If you have some classes or if you have any issue, then you can adjust the reducer length also. If you don't have any issue, you can consider the reducer length as 300 to 400 mm. So I have considered the reducer length of 400 mm. As we saw now, for the 400 mm duct size, it will be around 14 degree or 30 degree will come. So that is the reason after the 10 degree we have 15 degree. So I have gone to 15 degree for the selection, and here it is 1.25, and so we have to take the average of these two answers, that is 0.00, that is 0.00 plus 0.52. We have to take the average. So you can see 0.00 plus 0.52 divided by 2, so it is 0.26 the average answer. So I have to consider the same for the fittings coefficient for the calculation here. So 9.5 the velocity pressure, 0.26 the fitting coefficient from ASHRAE application handbook. So the answer is 2.47 Pascal for this reducer. So the first reducer is done, and we have to go for the second reducer now. So you can see the duct size here 450 by 200 at this point. After this branch it is reduced to 350 by 200, and the flow is 215 liter per second. So here the airflow 215 liter per second, and size at upstream 450 200 and 350 200. Just now I explained in the drawing these two sizes. And coming to the velocity pressure, first you have to go to the duct sizer. So duct sizer 215 liter per second I applied, and friction loss I applied, and duct size 350 by 200 at a lower downstream side, so that I applied. And you can see the velocity pressure, it is 6.69. 69. So that value I have to round off to 6.7, 6.69. So round off to 6.7. Now the important thing is we need to know the fittings coefficient again. So you need to find out the A1 by A0 as I explained in the earlier step. So A0 by A1 from the area which is coming from these two. A1 is equal to width into height, that is for this one, and A0 is equal to width into height for this one. And here one important thing you have to see the how to measure this A0 A1. For example, here you see it is H1 here they have given here, and H0 they have given here. And the important thing here is the fan direction. See, you can see from fan they have mentioned. So from fan only it is decided. For example, this side they have given A1 and this side they have given A0. That means this is the upstream side and this is the downstream side. So upstream side is always H1 and A1. So that is the reason upstream I have given 450 by 250. So in our case, for example, if you go to our FCU, so if you see here, so this is the fan direction. This is the fan direction which is coming from here. So that is the reason this is the upstream side. That means the A1, and here is the downstream side, that is the A0. So you have to divide by A0 by A1 to find out the answer. So in our case, if you see here, okay, so A0 by A1, so I divided by A0 A1 from downstream by upstream, so it is 0.78 is the answer here. And coming to the angle, as I told you, minimum length we can consider 400 mm for the initial case, so it will make approximately 14 degrees. So I have considered 15 degree from here, and this one is in between these two, 0.78. So again we have to take the average of these two answers, 0.00 and 0.05. So if you take the average 0.00 plus 0.05 divided by 2, it will be 0.025. So that one I have applied here. Velocity pressure into fittings coefficient, velocity pressure from the micro duct sizer, that we already find out. So it is equal to 0.17 Pascal for the next reducer. So now we finish this reducer, the next reducer also. You can apply the same concept for this reducer also. So you can try using the same method which I explained, so you get the answer also. So after the straight duct and reducer, I am going to explain one more important fitting here, that is this elbow. So you can see the elbow, the size is 300 by 150 and the flow is 108 liter per second. So I have given the input here. So 108 liter per second, and the elbow size is 300 by 150. The friction loss we are going to follow the same. The fittings head loss, as I explained you, for all the fittings we have one common formula, that is velocity pressure into fittings coefficient. You have to multiply with velocity pressure we can get from the duct sizer. For example, if you go to the duct sizer, the airflow is 108 liter per second. The friction loss is 0.6 Pascal. That is the constant value. And the duct size here is 300 by 150. So if you apply 300, it will be 125. 125 is not applicable to duct size. You have to go to the next nearest one, that is 150. And if you go to 150, you can see what is the velocity pressure here. That is 4.1691. You can round off to 4.2. So that is what I added here also. Now we need to know the important thing, that is fitting coefficient. So if you want to know the fittings coefficient value, here there are two important formula we have. The first one here is C0 is equal to K into KP, CP. So K is the angle factor. If you see the angle factor, so this is the 90-degree elbow we have in our project. So there are different factors. I mean, the angle they have given, like 30 degree, 45 degree, 60 degree, like that. So in our case we have 90 degree. So the K value will be 1. So now the another important thing, we have to find out the CP value. For the CP value, you see it's H by W. H means the height of the duct by width of the duct. So in our case, this is the width and this is the height. So how to find out height by width? That is 150 by 300. That is 0.5. So we can go with this 0.5 here. But the another important thing is R by W. R is the radius of the elbow and W is the width of the elbow. So if you see here the R here, the R they have taken from this point to the center. Okay, so normally the width in our case is 300. So if you measure the width from this point to this point, it will be 300. So but we are measuring the, if you see the radius here, from where to where we have measured here at this point. This point first from here to here, that if, for example, this is 300, the overall is 300, means the half of the 300 will be 150. But we have measured the radius from this end to this end. So this is 150, again this is 150. So total the radius is 300 mm for this case. So R by W means R by W is equal to 1, because in our case the width is 300, the R is 300, so R by W is equal to 1. So some project we will use the R by W is equal to 1.5 also. So you have to make sure that what is the R by W is there in the drawing. Okay, so mostly it will be 1 or 1.5 it will come. So here R is equal to W, R by W is equal to 1, because radius is 300, width is 300 already. So we have to go with this one. And here it is 0.5. So the answer is 0.25. So that is the fittings coefficient for our case. So 0.25, and already you know the velocity pressure. If you multiply both, you will get 1.05 Pascal. It's a friction loss. So here one important doubt will come to you, because if you see at this point, there are lots of branches are connected with the main duct like this. So should we consider the friction loss for this connection point, I mean the SU piece, or not? Actually saying, we don't want to consider the friction loss of this one. If something is in the path of the residential part, for example, we have to find out the ESP only for the longest path. Here the longest path is from here to till this point, at this point. So the FCU has to throw the air from here to till the all the way this point. If the FCU can throw the air to this point, surely if the FCU can throw the air to this point, surely it can throw the air to here, here and here also. So that is the only reason we are finding out the ESP for the longest path. And these are the branches which is touching the wall of the main duct, but it is not obstructing the flow. For example, if you have, if you have one volume control damper here, which is the path of the air flow, air stream. So that is the reason we have to consider whatever is there in the path of the duct, not in the branch. This SU piece, so we don't. That's the reason we didn't consider the SU piece. Let's say, for example, we have one volume control damper in the pathway. So how to perform the calculation for volume control damper? For example, in the same calculation, let me consider that the longest path is coming like this, which is going like this. So this is the longest route. So here we have one volume control damper. This duct is going straight like this. So we have one volume control damper here. The volume control damper, just for example, I'm telling. So because if you have something in your project, you would have to know how to find out. So here it is 108 liter per second, and the duct size is 300 by 150. So let's see how to find out. So here the size I have given 300 by 150, and airflow I have given. From the duct size that you have again you can take the 108 liter per second, and head loss same 0.6, and the velocity pressure it is was 4.16. So you can go to You can apply this one, the same formula, head loss equal to velocity pressure into fitting coefficient. And for the fitting coefficient, you have to go to the ASHRAE duct fitting database. Here you can see the damper with parallel blades. So here I have given the volume control damper snapshot. So here the theta is very important and L by R is important. So for the L by R, you have to go with this formula. But the initial practical thing is, at the time of starting, when you do this ESP calculation, you don't know how to adjust this, how much this angle will be adjusted, because this VCD shall be adjusted during the testing commissioning stage to balance the flow requirement. And that is the reason we cannot say that initially it is the angle is 30 degree, 40 degree, 50 degree. We cannot define at the very initial stage. So that is the reason always at the initial stage of the ESP we can consider the angle as 0 degree. So we are considering that the initial stage it is considered as a fully open, the volume control damper, so it is 0 degree. So if you say 0 degree, always this answer will be 0.52. So whatever the L by R, the value, the answer is 0.52. So we can directly take the answer 0.52 without going further to L by R, this type of very detailed. It's very simple. You can consider the 0.52 for all the answers. So 0.52 the fitting coefficient, you can multiply with the head loss, it will be 2.18. You can round up to 2.2. So this is the same concept you have to repeat for all the volume control damper if you have in your longest path. So now finally here we have four straight duct piece. For example, here 0.5 meter, 3 meter, 3 meter and 5 meter. So all this pressure drop we added here. And coming to the reducer, we have one reducer here that I already showed you, and we have another reducer that also I showed you. We have one more reducer. This one you can try using the same formula, so you can get the answer. So for time being, I consider the second diffuser pressure drop as third diffuser, but if you do the actual calculation, it will be slightly different. So this is the diffuser pressure drop. And coming to the elbow, we have only one elbow. That pressure drop I added here. So next, the important thing is the final one, that is the air terminal, or you can say here the square diffuser. So square diffuser, I explained you how to select the square diffuser considering the static pressure, neck velocity, throw and different factors. I have posted a separate video. Please have a look at that. And normally it is general practice that the static pressure pressure drop we normally consider like maximum 10 Pascal. Some project it is going we are going with it 15 also if consultant doesn't have any special requirement. But it is a good engineering practice that you can consider the maximum pressure drop as 10 Pascal for the square diffusers. So the total pressure drop I am adding all, so you will get 19.783 Pascal, and finally the safety margin minimum 10% you have to consider. So final pressure drop will come 21.76 Pascal. So when you go for the selection, you have to inform this value is external static pressure to the manufacturer for the proper selection of FCU. So other than this proper workout, when we go for the IFC drawing, you might have seen that there are different ESP value is given in the IFC drawing issued for construction drawing. So when we prepare the drawing, normally what we do, we will not do that much detailed ESP calculation for each FCU or each AHU for at the initial stage of the project. So that's why we will normally consider one standard value, like for the FCU 50 Pascal we always put in the IFC drawing. So AHU and FAHU we can add 500 Pascal and package unit 250 Pascal, and below that we will provide in the notes, that in the notes we will mention that contractor has to verify the HVAC unit external static pressure after finalizing the shop drawing. So this notes we will mention, and we will finalize the ESP at the time of issued for construction. When it comes to the shop drawing and further ordering the material, then you have to verify the ESP for each and every material, each and every unit. So thank you for watching the video. If you have any doubt, please add your comment in the comment section. Thank you. Bye bye.